We're going to be using that today. Linear pairs look like a line with an array coming out of the middle, kind of like a Y shape. And because it forms a straight line, it's supplementary, which means it adds to 180 degrees. So that's what our video for you today is brought to you by. We're on page 329, and so if you have your math book, if that's what you're using for a math resource, we're continuing the lesson on the sum of the measures of the exterior angles of a polygon. We're pushing for a formula or some sort of observation that we can use to maybe find the measures of one exterior angle of a polygon. If you're ready for this lesson, you have a highlighter. You actually have a straight edge because in the first part of this video, you need to create a quadrilateral, a pentagon, a hexagon, and then you need to also extend the side of the shape in a direction, consistently in a direction, so that you are creating exterior angles. Like, I didn't really measure how I made this quadrilateral, just make sure it has 4 sides. Quadrilateral, 4 sides. A pentagon, that's Greek for 5 sides, and a hexagon, Greek for 6 sides. So I'm going to show you how I created the exterior angle. I'm taking my line, and I'm kind of making like that fan shape where I go in a consistent like direction. In this case, I'm going counterclockwise. So I went that way, that way, that way. I haven't drawn this exterior angle for my pentagon, so here's how I'm going to do it. Line up. There it is. You can kind of see it like fan wrapping around in a certain direction, and I'm missing my exterior angle here. There we go. All right. It would probably be wise to draw some or add some information to this one. Let's go ahead and complete 3, 4, 5, and 6 out of the table, given what's here. Calculate the sum of the measures of each polygon's exterior angles by extending each side of the polygon to locate an exterior angle at each vertex. That needs to be a word for the wall. The vertex are the corners. Complete the table for 3, 4, 5, and 6-sided polygons. Well, you know what we just did for triangles. So the sum of the measures of the linear pairs in a triangle is 540. If you didn't know, it's on the other page. Take a look at page 328. Go back to that video and take a look at it. The sum of the measures of the interior angles is 180. We did that on the previous 2 pages, right, where we talked about the interior angles of a polygon. If you happen to find the sum of the measure, you can subtract these in order to find the sum of the measure of the exterior angles. It's 360 again. Shout out page 328. Go look at that video. But how about in a quadrilateral? You see, in a quadrilateral, you have linear pair, linear pair, linear pair, linear pair. That's 4. For the 4 corners, that's 4 places where you have 180 degrees. So 4 times 180, 720. Well, we also know from the previous page, flip back to a table that we made on page 326 and 327. The interior angles of a quadrilateral add up to 360. It was that whole idea about how you could draw a diagonal from one vertex to its opposite vertex and create 2 triangles, and you add them up. Go watch the video. If you subtract these 2 numbers, you get 360. Let's do it for the pentagon. Same idea, right? Same idea. So you have linear pair, linear pair. Remember, that is the vocab word of the day, linear pair. And let's see, linear pair, linear pair, linear pair. 5 linear pairs, 180 for each of them. 5 times 180 is 900. A little refresher reminder, the sum of the degrees in a 5-sided shape is 540. You add them all up. So 540 is the sum of the measures of the interior angles. Subtract, what do you get? For sure. How about for a hexagon? For a hexagon, you have linear pair, linear pair, linear pair, linear pair, linear pair, and linear pair. All hexagons. Yours that you drew that are different than mine. We all drew different hexagons if you're drawing, following along with me. So there are 6 180-degree linear pairs. And if you multiply them out, you get 1080. Now, from the previous page, the sum of the angles on the inside of a hexagon is 720. Do some subtraction. 360, there you go, that's our table. We'll do 7 and 15 next. But the sum of the exterior angles is 360 degrees. Again, assuming that you're only creating them from one like one exterior angle per vertex. There might be some other ways you could draw exterior angles. Just be consistent as you extend the sides out to create the exterior angle. Let's go ahead and actually do it for a 7-sided figure, right? We got to project here. How do you see 540, then 720, then 900, then 1080 changing? What are they growing by? Like 3, 4, 5, 6, 7 is going up by +1, but what are these going up by? That's right, they're going up by 180 degrees. So 1,280 degrees is the sum, 80, 60, oh my goodness, 60, is the sum of the measures of the linear pairs. Now, from the previous table, I believe we did talk about a heptagon. The sum of the measures of the interior angles is 900, so we can write that right here. And you subtract, right? 1,260 minus 900, we should already know it's 360. In fact, we can fill that in right here. We know it's going to be, for a 15-sided shape, the sum of the measures of the exterior angles is going to be 360. We can work way backwards, though. I think what we did in the previous lesson. To calculate this number, it's 15 minus 2 times 180. Okay? 15 minus 2, that's the number of diagonals you can draw off of one vertex for a 15-sided shape. Hey Siri, what is 13 times 180?
13 times 180 is 2,340.
Okay. The sum of the measures of the linear pairs, you know what? It was 3 linear pairs, 4 linear pairs, 5 linear pairs, 6 linear pairs, 7 linear pairs. So there must be 15 linear pairs. Hey Siri, what's 15 times 180? Bear with me. Hey Siri, what's 15 times 180?
15 times 180 is 2,700.
And if you subtract, you get 360 again, so everything stays consistent. What is then the sum of the measures of the exterior angles of an n-sided? It doesn't matter how many sides there are. What will every single polygon, what will the angles add up to for every single polygon? Is it clear? Thank you for watching this video. Page 330 is next. Something for you to think about. Is this true for all polygons? Does it only work where all of the sides or angles are the same? If you look at these, are these considered regular polygons, or are they just random, arbitrary? Like I drew them, I wasn't measuring. You drew yours, you weren't measuring. But you did it with straight lines so that they at least had some precision. It's true for all polygons, no matter, convex polygons, no matter the size or angle measure along the way. Thank you for watching this video. See you in the next video. Thank you for learning and getting smarter in mathematics. One video, one day at a time.